This is the heat resisting alloy assignment for SSM. My name is M.Azhar Aditama, name 1311825, and let's get on with it. The topics we're gonna cover is the creep phenomenon and classification, the Larson-Miller parameter, heat resisting alloy microstructure. Firstly, I'm gonna talk about the creep phenomena. To start off, I'm gonna explain the definition of creep. Creep is the time-dependent and permanent deformation of materials when it is subjected to a constant load or stress. It is known that creep is not wanted, as it is a limiting factor for how long an object lasts. So materials are often placed in high temperature and exposed to statical mechanical stress in, for example, industries. This kind of deformation is also defined as creep. We can see from this diagram there is 3 regions of creep, which is primary, secondary, and tertiary. Each of these regions have its own distinctive strain time feature. The first region is the primary region, which is a slope of the slope of the primary region decreases with time, as you can see. This decreasing slope suggests that the material is experiencing increase in creep resistance or strain hardening, and therefore the material is much more difficult to be strained or elongated. For secondary region, the creep rate is constant. So as you can see, the plot is linear, it's a straight line. This stage of creep is usually the longest time, since as you can see the region is much longer than compared to primary or tertiary. This constant creep is due to computing processes of strain hardening, recovery, and recrystallization. This 3 process is basically a annealing process, which makes a material more softer, and also it retains its ability to experience deformation. And lastly, for tertiary creep, which is this region, there is an acceleration of rate and ultimate failure. As you can see, the slope increases. This failure is due to rupture. This rupture is an example of this rupture is basically grain boundary separation, and all of these. Also we can see from this figure 8.30, as you increase the stress or temperature from this, this increase in temperature or stress causes the instantaneous strain of the time at the stress application to increase. The steady state creep rate increases as well, and the rupture lifetime decreases. From all of this information, we know that creep characteristics allow a material to help engineers to suspect the lifetime or sustainability of a material for a specific application. Next will be the creep classification. There is 3 types of creep classification, which is Coble creep, Nabarro Hearing creep, and power law creep. Coble creep is basically a form of diffusion creep, It's a mechanism for deformation of crystalline solids. Cobalt creep also occurs through diffusion of atoms in a material along a green boundary. We can see from here, this is a diagram of cobalt creep when the material is applied by actual load, actual stress. We can see the direction of the grain diffusion of atoms. Next will be Nobarro hearing creep. It's a mode of deformation of crystalline material and also amorphous material that occurs at low stress, and it is also held at high temperatures in a fine grain material. Nobarro hearing creep occurs through lattice diffusion. Now, this is also the diagram of Nobarro hearing creep in comparison to cobalt creep. Cobalt creep is they're both similar, cobalt and Nobarro hearing creep, in ways that cobalt creep is more dominant at lower stress level and higher temperature than the creep mechanism that utilize dislocation gliding. And the last creep classification is the power law creep, which dominates at high stress. The creep strain rate of power law creep is determined by the rate at which the dislocation are able to climb over obstacles. By obstacles, it can be the green boundary or the impurity of a substance. The next topic will be the Larson-Miller parameter. This is basically a method of data exploration which will fulfill the need of increasing creep data that are impractical or difficult to collect from like a normal lab test. The Larson-Miller parameter predicts the lifetime of a material against time and also the temperature using an approach that is based on the Arrhenius rate equation, which is this equation. M is basically the Larson-Miller parameter, T is the temperature, and C and TR, C is basically the material constant, and the rupture lifetime is equals to TR. This is an example of the Larson-Miller parameter that is taken from the book. So the question asks, using Larson-Miller data for the specific alloy, predict the time to rupture for a component that is subjected to stress of 140 megapascal at 800 degrees. So from the figure of 8.33, and we estimate the value of 140 megapascal on that figure, we know that the value of Larson-Miller parameter is 24 times 10 to the power of 3, and we also know the temperature and K as well as TR from the question, and thus we just substitute the values in the Arrhenius rate equation or the Larson-Miller parameter, and we get the time for rupture of this S590 alloy. Next, and the final topic will be heat resisting alloy microstructure. There are factors that affect the creep characteristics of a metal, which includes melting temperature, the elastic modulus, and grain size. From the pattern of melting temperature, we know that the higher the temperature, the greater the elastic modulus, and also the grain size also increases. This will increase the material's resistance to creep. In terms of grain size, the relationship is that the smaller grains permits more grain boundary for sliding, in which causes the grip to increase. This effect can be referred to the grain size of mechanical behavior at a lower temperature. Advanced processing techniques have also been utilized, and an example of this technique is a directional solidification, which is this process. This process produces highly elongated grains or single crystal components, which is this image. This single crystal is a material in which the crystal lattice of the entire substance is continuous and unbroken to the edges of the sample, and therefore there are no grain boundaries. This is the image of a single crystal. We can see that it has unbroken edges and also no grain boundaries. And finally, the Equiax crystal, which is this image. The crystal have the axis. Each of these crystals have an axis that have the same length. Equiaxed grains can also be an indication for crystallization. From this figure, we can also see that the lengths of this grains are the same. This is the smaller equiaxed grain, and this is the larger equiaxed grain. Thank you for listening to this part of the presentation.